Hello, my precious friends. I really hope that you are doing great. Welcome to our today's class. It's our first lesson on the sixth topic of Form 3 work, which is called Waves 2. As usual, let me commence by giving you the quote of the day, which states that it doesn't matter how slow you walk, provided that you don't stop. We shall discuss that quote at the end of our class today. So today we are looking at waves 2, meaning that we had waves 1. So to understand waves 2 better, I will advise you to go back and watch our videos on waves 1 so that you'll be in a position to understand waves 2 better. So under waves 2, we'll basically be looking at the four properties of waves, that is reflection, refraction, diffraction, and interference. So let's start by looking at how the waves can be studied in the laboratory. So the properties of waves can be studied in the laboratory using a ripple tank. So a ripple tank is just a tank that we fill with water. Then the ripple tank consists of a transparent tray containing water. The purpose of the transparent tray is to allow the formed water waves to be reflected. So they allow reflection of the water waves. Then it also has a point source of light which simply illuminates the waves that have been formed so that they can be reflected. Then it also has a white screen underneath. The purpose of the white screen is just to display the formed waves. Then it also has a small electric motor or a vibrator which acts or generates the waves. So remember, when they vibrate, when the electric motor vibrates, it simply generates the waves. Then it also has a hand stroboscope, which is just an instrument that we use to observe the formed waves. So the wave pattern is usually represented by wavefront lines. So these lines usually connect all points that are in phase as the wave moves. So if you're asked to define what we mean by wavefront lines, you simply say that these are lines that connect all points that are in phase as the wave moves. So remember, in phase we discussed points being in phase under waves 1. So in case you still don't understand what we mean by points being in phase, you can just review our lessons on waves 1, which was our third last topic under Form 2 work. So under this particular topic, that is waves 2, we'll be representing waves by wavefront lines. So you can see in this particular diagram, so if this is our transverse wave which is moving towards the right hand direction as shown, we have the wavefront. So these particular lines which are actually perpendicular to the direction of motion of the waves are what we call the wavefronts. So this is our first wavefront, we have our second wavefront, we have our third wavefront. So you can see that the wavefront is simply occurring at points where any 2 points are actually in phase. So we have said that wavefronts, they usually connect all points that are in phase as the wave moves. Remember, a point will be in phase after a wave has actually formed a complete cycle. For example, if I start from this particular point, this is half an oscillation plus half an oscillation. So it gives us a complete circle. So after a complete oscillation or after a complete cycle has been formed, the second wavefront will occur. So after also, if we start from this point, this is half a cycle plus half a cycle, we form a complete circle. So after a complete oscillation or after a complete cycle, that is when the wavefronts will occur. That is why we are saying that wavefronts are lines that connect all points that are in phase on a wave. Then a point will be in phase if a complete oscillation has been formed. So again, that simply tells us that the distance between any successive wavefronts, between any two successive wavefronts, will actually be equal to one wavelength. Because remember, under waves 1, we defined wavelength as the distance between any 2 points on a wave, the distance between any two successive points or on a wave that are in phase. So because the distance from this point up to this second point here, that is the distance after a complete oscillation has been formed. So the distance covered, we defined it as the wavelength, that is from waves 1. That is the distance between any two successive points on a wave that are in phase. And we are also saying that that particular distance is also equal to the distance between any two successive wavefronts. So that simply means that the distance between any two successive wavefronts will be equal to one wavelength. So one wavelength is simply equal to the distance between any two wavefronts. So we are saying therefore the distance between successive wavefronts is simply equal to one wavelength, because a wavelength will always be formed if any two points, any two successive points on a wave are in phase. Then after understanding that a wavefront, any two successive wavefronts will give us one wavelength, let's look at the four properties of waves. So the properties of waves, one, we have reflection, refraction, diffraction, and interference. So in this chapter, we'll just be discussing these four properties of waves. So let's start with the first property, which is the reflection of waves. So remember, to understand this better, you can also review, that is reflection at curved surfaces, or rectilinear propagation of light. So under light, we did define reflection as the bouncing back of light when it hits an obstacle. However, in that case, we were only looking at one wave, which was the light wave. But in this topic, we'll be looking at different types of waves. For example, we can have the light wave, we can have the water waves, we can have the sound waves, we can have the radio waves, etc. So reflection in waves occurs when the wave is bounced back at the wavefront position, just like in light, whereby the reflection was simply the bouncing back of light when it hits an obstacle. Now for the case of the waves, that is the waves, the combined category of waves, we said that reflection of waves, it occurs or is simply the bouncing back of waves at the wavefront position. Then rectilinear propagation of waves is simply a property of waves traveling in a straight line and perpendicular to the wavefronts. Remember, under Form 1, that is under rectilinear propagation of light, we did say that is simply a property of light which suggests that light travels in a straight line. But for this case, we are looking at all type of waves. So rectilinear propagation for the case of waves will simply be a property of waves which suggests that the waves travel at a straight line, and that is a property of waves traveling in a straight line, in straight lines and perpendicular to the wavefront. So you can see the direction of motion of our wave. In this particular case, the wave is moving from the left towards the right hand direction. The direction of motion of our waves is actually perpendicular to the wavefront. That is the angle between the wavefronts, and the direction of motion of the wave is actually 90 degrees. So the angle between the wavefront and my wave is 90 degrees. That's why we are talking of perpendicular to the wavefronts. Then the reflection of waves obey the laws of reflection of light. If we can just remind ourselves from Form 1 work, we did say that the two laws of reflection of light is that the first one was that the incident, that is the angle of incidence, must be equal to the angle of reflection. Then the second property, or the second law of reflection of light, we did say that the incident, that is the incident light, that is the incident light, the reflected, that is the incident ray, the reflected ray, and the normal at the point of incidence occur, that is, occur on the same side of the reflecting surface or on the same plane. That is the incident ray, reflected ray, and the normal occur, that is, and the normal at the point of incidence occur on the same plane. So similarly, for the waves, we shall say that the incident wave, the reflected wave, and the normal at the point of incidence occur on the same plane, or occur on the same side of the reflecting surface. Let's look at reflection of some of the waves. So we are saying that the nature of the reflected wave usually depends on the shape of the reflecting surface, that is as shown below. So consider our wave here. So it is traveling from the left hand direction towards the right hand direction. Then we have a reflecting surface here. Then of course the wavefronts will always be perpendicular to the direction of the wave motion. Then we have said from a previous slide that the wavelength will be equal to the distance between any two successive wavefronts. So also to understand it better, remember that from the laws of reflection of light, the angle of incidence must be equal to the angle of reflection. Then first of all, we are looking at plane waves on a straight line, that is on a straight reflector at an angle of 90 degrees. So the plane wave simply means the straight waves. So you can see the wavefronts are representing our plane waves. So these are the wavefronts or the incident rays. So these are the incident waves, which are simply traveling from the left-hand direction towards the right-hand direction as indicated by this particular arrow. So the ones in green are our incident waves. So remember, when an incident wave meets the reflecting surface, it will be reflected in the opposite direction. Just like for this case, if you have an incident ray being reflected on a plane surface, it would be, that is, if it was moving towards the right hand direction, after reflection it will be moving towards the left hand direction. Similarly, if you have a ray which is perpendicular to the reflecting surface, remember, a line perpendicular to the reflecting surface, we call it the normal. So for this case, we are talking of a straight wave or a plane wave on a straight reflector at an angle of 90 degrees. So it simply means that our incident waves are meeting the reflecting surface at an angle of 90 degrees. And we know that a line which meets the reflecting surface at an angle of 90 degrees, we call it the normal. And if you have a ray which is parallel to the normal, it will always be reflected through the same normal. So if this is our incident ray, if it hits the reflecting surface at an angle of 90, it will be reflected through the same path, such that this will be the reflected ray and this will be the incident ray. So the same thing happens here. We have the incident waves which are traveling, that is, perpendicular, or which are meeting the reflecting surface at an angle of 90 degrees. So upon reflection, because they were moving in this direction, after reflection, they'll be reflected through the same path, but towards the left-hand direction, such that the incident waves were moving towards the right-hand direction. After reflection, they'll be moving towards the left-hand direction. So these particular dotted lines in purple are representing our reflected waves. So these are the incident waves, but after reflection, the reflected waves will take the shape of the reflecting surface, because we have said that the nature of the reflected wave will always depend on the shape of the reflecting surface. So for all plane waves, or for all straight waves, they will be reflected in such a way that they take the shape of the reflecting surface. So you can see our reflecting surface is a plane wave, or it is a straight reflecting surface. So after reflection, you can also see that the reflected waves are also perpendicular, or they are also straight waves. So the reflected waves will always take the shape of the reflecting surface for any plane wave. Then 2, we look at plane waves on a concave reflector. So again, so these are the plane waves or the straight waves which are being represented by this particular, the wavefront. So these are the incident waves. So we have said that for this particular topic, we'll be representing the waves by the wavefront. So these wavefronts which are in color green are representing our incident wave. So when the incident waves or plane incident waves, when they meet a concave reflecting surface, they'll be converged. Remember, from reflection at plane surfaces, that is in form 2, that is when we were looking at reflection at curved surfaces, we did say that concave reflectors or concave mirrors are also called converging mirrors, such that any rays coming to a concave mirror, it will be converged at a common point. So similarly, for this case, the incident waves, which are straight waves, when they meet our concave mirror or the converging mirror, they'll be converged at a common point. So the ones in green are representing our incident wave, which are traveling as shown in this particular direction, that is, they are traveling towards the mirror or towards the right hand direction. Then after reflection, as we have shown here, after reflection, the waves will be moving towards the left hand direction. So if the incident wave was moving towards the right, after reflection, it will move towards the left. So similarly, our incident wave were traveling towards the right hand direction. After reflection on the concave mirror, the reflected waves will take the shape of the reflecting surface, because we have said that the nature of the reflected wave depends on the shape of the reflector, that is for the plane waves. So after reflection, we expect the reflected rays to take the shape of the reflecting surface. So because the reflecting surface is concave in shape, that's why the reflected waves or the reflected wave fronts are also in concave shape. Then you can see the incident wave were moving towards the right hand direction, but after reflection, the reflected waves or the reflected wave fronts are moving towards the left hand direction, as indicated by this arrow and also this arrow here. So they are reflected in such a way that, 1, they take the shape of the reflecting surface, then they'll be converged at the focal point, or at F, because this is a concave wave which tends to converge the rays of light at a common point. So for this case, the waves will be converged at a common point. So maybe in an exam situation, you'll just be given the incident waves, then you'll be asked to draw the diagram to complete and show how the reflected waves will form. So if they are plane waves, just remember that the reflected waves will take the shape of the reflecting surface. So if the reflecting surface is concave in shape, then the reflected waves will also be concave in shape. So you can see the ones that are in color purple. So these ones are representing the reflected waves, which are also in similar shape with the shape of the reflecting surface. Then if it is a concave mirror, they will be converged at a common point, that is at the focal point. So we are saying that the waves converge at a point F, that is the focal point, in front of the reflecting surface. Hence, the concave reflector has a real focus. Remember also under reflection at curved surfaces, that is under Form 2 work, we did say that concave reflectors will always have their principal focus in front of the mirror, meaning that most of the images formed will actually be real. That is, they are formed in front of the mirror or on the mirror. So a concave reflector will always have a real focus because the F is in front of that particular mirror. So the reflected wave will take the shape of the reflecting surface, that is the concave shape. Then the direction of motion will be opposite to the direction of the incident wave. As we have seen, the incident ray, if it was moving towards the right, the reflected ray will be moving towards the left. Similarly, our incident wavefronts were moving towards the right-hand direction. After reflection, the reflected wavefronts are moving towards the left-hand direction as indicated by these particular arrows. Then Roman 3, we look at plane waves on a convex reflector. Remember, a convex reflector is just the same as saying a convex mirror, and we know that convex mirrors will always diverge the rays of light falling on them. But for this case, we are talking of the incident waves. So if we have plane waves, plane simply means straight waves. If you have straight waves meeting a convex reflector or a diverging reflector or a diverging mirror, they'll be diverged. So we have said that for all plane waves, the reflected waves will take the shape of the reflecting surface. So because our reflecting surface is convex in shape, the reflected waves will also be concave, that is convex. They will take the shape of a convex mirror. So you can see the shape of the reflected wave is similar to the shape of the reflecting surface, which is convex in shape. So, and a convex mirror or a convex reflector is always a diverging reflector. So you can see after reflection, the waves are being diverged. That is, they appear as if they are emanating from a common point F, which is behind the mirror. Then they are being diverged towards the right-hand direction. Similarly, if the incident ray is moving towards the right, the reflected ray will always move towards the left. So you can see our incident waves are moving towards the right-hand direction, that is towards the mirror. But after reflection, the reflected waves are moving towards the left-hand direction as indicated by this particular arrow. So these are our reflected wave, which are taking the shape of the reflecting surface. Then you can see they are reflected in such a way that they appear to be emanating from a point behind the mirror, which is our focal point. So remember also under reflection at curved surfaces, we did say that convex reflectors or convex mirrors or diverging mirrors will always have their principal focus behind the mirror. So the waves appear to be diverging from a point F behind the mirror. So this simply shows that the convex reflectors have a virtual reflector. Remember, virtual simply means that it is formed behind the mirror, or it is formed by imaginary rays or by rays which are not real. So again, in an exam situation, you'll be given the incident waves, then they'll ask you to sketch the reflected waves. So just remember that the reflected waves will take the shape of the reflecting surface. That is, if the incident waves were plane, then they'll be moving in opposite direction to the direction of the incident waves. Next, we look at circular waves on a straight reflector. So if you have a circular wave, remember for all plane waves, the reflected waves were taking the shape of the reflecting surface. But for the circular waves, it is actually different. So if you have a circular wave emanating from this particular point, so these are our incident circular waves. When they meet a plane surface or a straight reflector, they simply their direction of motion will simply change. So they are emanating from this particular common point, moving towards the right hand direction. After reflection, they will move towards the left hand direction. So the ones in dotted are representing our reflected waves. So just like in this particular diagram, if you have an incident ray moving towards the mirror, after reflection, actually the ray will be moving away from the mirror. That is, if it was moving towards the right hand direction, after reflection, it will move towards the left hand direction. Similarly, if you have a ray which is meeting your mirror at an angle of 90 degrees, that is moving towards the right hand direction, after reflection, the ray will be moving towards the left hand direction. So our incident ray was emanating from this point, moving towards the mirror or towards the right hand direction as indicated by this particular arrow. But after reflection on the mirror, the waves will now be moving towards the left hand direction as indicated by this particular arrow. So the rays in purple represent the reflected wave, but the ones in color green, they simply represent our incident wave. So again, you'll be given the incident waves, then you'll be asked to sketch the reflected waves. So you simply, the waves will simply change their direction of motion as indicated here. Then lastly, we look at circular waves on a concave reflector. So a concave reflector will make the circular waves into a plane wave. So if these are our circular waves which are emanating from this particular point, moving towards the mirror or moving towards the right hand direction, after reflection we expect them to move towards the left hand direction, just like the reflection of rays. So they were moving towards the right hand direction, but if they meet a circular wave, the circular wave will make the concave, that is the concave reflector will make the circular waves into plane waves. So the reflected wave will be the plane waves moving in opposite direction. So you can see the direction of the reflected waves is actually towards the right hand side, but the direction of the incident wave was towards the left hand side. So for circular waves on a concave reflector, they will be reflected in the opposite direction. Then the circular waves will be converted into plane waves. So plane simply means straight, as indicated by this particular straight wave fronts. So to understand this chapter better, just relate it with reflection at curved surfaces. You also relate with waves 1. So again, in an exam situation, we will be given the incident waves. Then they'll ask you to sketch the reflected waves. So you simply sketch the waves in purple, in color purple. Those are the reflected waves. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that it does not matter how slow you walk, provided that you don't stop. So the quote is reminding us to focus our mind on daily progress. So the quote is also encouraging us to be persistent in our small positive actions each day, because our long-term success is the sum total of each day's small achievement. Remember that the easiest way of accomplishing a huge task is by breaking it down into small achievable tasks. And lastly, recall that the struggle you are undergoing through today is developing the strength and the mental toughness that you will need tomorrow. So never give up, keep working hard, and your future is bright. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you will get notified. Until next time, this is Kind Tuition Academy.